In this video, I want to talk about resistors in parallel. And in this circuit above, resistances R1 and R2 are in parallel. And the reason why we say that they are in parallel is seen by looking at what is the voltage applied across R1 and R2. So what is the voltage across R2, let's say? So if you want to look at the voltage, you need to know what the voltage at this point is and what the voltage at this point is, right? So what's the voltage at this point? Let's call it A1. What's the voltage at A1? It's the same voltage which is applied here, A, because A and A prime are connected just by a wire, and this wire denotes an equipotential line. So the potential at A1 and A2 are the same. Similarly, the voltages at B, B1 and B2 are the same. So to get the voltage across R1, you need to find out what the voltage at A1 and B1 is. But the voltage at A1 and B1 is exactly the same as the voltage at A and B respectively, and therefore the voltage across R1 is V. Similarly, the voltage across R2 is also V, and the voltages across all these three components is exactly the same voltage, and therefore they are said to be in parallel. Okay, so now we know the voltages across each of these components. What happens to the currents? So the current starts to flow out of the power supply. It flows through this wire, and when it reaches this junction, it has two paths to take. The current, some of the current can flow like this and go through resistance R1, and some of the current will flow through here and go through resistance R2. Let's call this current I2, and let's call this current I1, and let's call the total current I. Okay, and then this I1 is going to flow through here, I2 is going to flow through R2, down here, down through this, and when we come back here, both this current I1 and this current I2 are going to combine and flow back. And as we said before, the current that's flowing out of the power supply has to be the same that is flowing into the power supply. So basically, we can write I equal to I1 plus I2, right? Okay, but what is I1? I1, if you look at resistance R1, is this voltage divided by this resistance of that resistor. So we could write the current I1 as V over R1 and the current I2 as V over R2. And we could just take this V as a common factor and say that this resistance is 1 upon R1 plus 1 over R2. Okay. Now if I just wanted to find out what the total resistance offered by the combination by this to this power supply is, that is, if you combine R1 and R2, what's the effect? I could write that I could find that out by finding out what V over I is, right? Because what is V? V is the voltage of the power supply here, and I is the current that is going out. So what is the resistance that this circuit is seeing? So if I write V over I, what I find is that V over I from the equation that we have becomes equal to 1 over R1 plus 1 over R2, right? And let's call this as equivalent resistance. Now, what do we mean by equivalent resistance? So let me just draw and show you. So if I could replace this entire circuit that I have drawn on the screen here with this kind of a resistance, if this kind of a circuit. So I have a voltage source V and I replace it with one resistor instead of the two resistances. And this, the value of this resistance is R equivalent, right? So what is the value of R equivalent going to be? Well, to find that out, let's write what is V over I for this circuit going to be. So V over I for this circuit is going to be R equivalent. So we can work this out by looking at the equations here. So what is R equivalent going to be? So R equivalent, or more accurately 1 over R equivalent, is equal to 1 over R1 plus 1 over R2. So let's summarize what we thought about in resistors in parallel. So if we have a voltage source and two resistors are connected to it, it could be more than two, such that the same voltage is applied to both these resistors. The two resistors are said to be in parallel. Okay, so the point number one is that it has to be the same voltage applied across the resistances. If that is the case, then the equivalent resistance, R equivalent, is given as 1 over R1 plus 1 over R2. Okay, and the resistances through each of these branches, and I'll leave that for you to prove, is I1 is equal to I times R2 by R1 plus R2, and I2 would be equal to I times R1 over R1 plus R2. So there is a current division that starts to happen, but the current division, so the current that flows through R1 is proportional to the value of R2, and the current that goes through R2 is proportional to the value of R1. So it's kind of inversely proportional in some sense. So now think about this application that we had discussed some time back, and we are saying that there is a 120 volt, there's an electrical device that works on 120 volts, and because of some fault there is a short between the 120 volts and the casing. Because of that, the person is actually touching 120 volts because this casing has become live, right? But thankfully the casing is connected to ground as shown here, but the person is also connected to ground. So the current in this device is going to go through the person to the ground, and also some of the current is going to go through the ground safely into the ground. So there are two paths that the current can take. So we could draw this as something like this. So you have an 120 volts source, and you have one path, which is the path that is here from this point down to ground. Okay, so, and that offers some resistance to the current, and let's call that resistance R ground. And then there is another path for the current to flow through the human being. So that resistance, let's call it R body. Now, and associated with this, there's going to be a current flowing through here to the ground and through the human body, let's call it IB. Now, if we want that the current IB is as small as possible, what would we have to do? To make IB as small as possible, remember what will be the equation for IB? IB will be equal to the total current I times R ground divided by R body plus R ground. right? So to make IB very small, what we want is we want this R ground to be as small as possible and this R body to be as large as possible. And so if our ground connection is well made, that is, there is a connection here and the connection is properly done, then most of the current will go through this and very little current will go through the body, and hence the person will not get a shock. But let's say this ground is not properly connected or it is not there, which means that your R ground is infinite, then all the current is going to go through the human body and that person has a chance of getting a shock. So there's one way in which current division can literally save your life.